We'll go into Spark a little bit. What about OpenShift? Great. Okay, awesome. This will be good. So I'm going to start first by talking about what is cloud native, since we have it in the title. And I'm using a definition that comes from the Cloud Native Computing Foundation. And what they say is that a cloud native application should be something that's containerized, so the application should be built in a container. And following from that, it should be dynamically orchestrated. And what that means is that that container could be moved between platforms that accept containers. And then likewise, kind of philosophically or ideologically, you should build your application in the manner of a microservice. And this is a buzzword that's very overloaded these days, but it just means to build it in a simple way that can input and output and do kind of one thing and built for this service approach. And if you're curious about their definition or more about these, I'd recommend going to check out their website. They have a good FAQ and more resources there. So speaking of cloud native, OpenShift is a cloud native platform. And what we're looking at here is kind of the general architecture of OpenShift. Now, it seemed like most people are familiar with it, so I'll just go over kind of quickly. OpenShift is a community packaging of Kubernetes. And so what we have here, what we're looking at is these are all containers using the Kubernetes language. They're put into pods, and then these nodes are actually correspond to where the work is done. And in this diagram, you can see that OpenShift can sit on top of a service layer, and that service layer could be physical machines, it could be virtual machines, it could be some sort of private cloud. So really, OpenShift can live on top of other things. It could be OpenStack, it could be anything. And then at the top, you can see this like a routing layer for exposing services and whatnot. So this is just a general view of what OpenShift looks like in terms of architecture. So how does that relate to Apache Spark? Well, the way that we've been looking at this is containerizing Apache Spark. And so in general, you might see these on your nodes. These are the actual containers that live inside the platform. And you might have a Python application, and you might have several Spark nodes so that Python can talk to it. Maybe you have another Python service over here, Mongo database. This is what an application might look like as deployed on a cloud-native platform. So let's get into Spark now. Again, it seems like many people here are familiar with Spark, but in general, this is what a Spark application will look like. And at the bottom here, we have a cluster manager. And Spark can talk to several different backends. There's many different ways to have it manage the workers that are involved in the processing. And so the way applications are created is we have what's called a driver process, and this is how we refer to the application where your user code will be. And within the driver process, there is a Spark session. That session allows you to communicate to the distributed cluster that will do the work for you. And the work is done by executors. This is the parlance that's used within the Spark community. And those executors could be running on virtual machines, they could be in a container. They're separate processes that will run. So how would you interact with Spark? For those of you who are familiar with this, you've probably seen this before. The Spark submit command comes with Spark, and it's a real easy way just to pass in a file and run it. So in this case, we're looking at something called myapp.py, just a simple file. I tell Spark to run it. It will distribute that task across all of the executors. And in this case, you can see I'm passing a master command in. I'm just telling it that in this case, I would like it to use the local machine and a single core. So this is very flexible. I could give it a URI to a remote master, and then it could talk to Spark in that manner. So it's very flexible what you can do. There are many more commands you can get into. Another way you might interact with it is using a REPL. So a read, evaluate, print loop. Has anyone here, who here is familiar with REPLs? All right, some people. Has anybody just run the Python command from the command line and see it come up? So that's a REPL. You can type in a command, and it will give you output based on what your command is doing. So it's a very easy way to evaluate a program. Well, Spark has 3 really nice REPLs. There's one in Scala, one in Python, and one in R. And what these allow you to do is you can run the command, it will connect to a Spark cluster for you, and then you can manually type in the program that you want, and you can see the reaction coming back. So it's a really easy way to evaluate what you're doing with your program, because you can manually step through each line that you want. You can evaluate objects as they come back. If you haven't run the Python command just by itself, I would highly recommend doing that. It's a really easy way to introspect the programs that you're creating. So in Spark, there is a fundamental abstraction that kind of sits at the base of all the data processing that you're going to do. And that is called the Resilient Distributed Data Set, what people refer to as an RDD. And that underlies most of the abstractions that occur in Spark. And what it is it's a partitioned, lazy, immutable, homogeneous collection. Now that sounds like a mouthful, so I'm going to go through it piece by piece. It's partitioned, meaning that your data can be segmented so that it can be sent out to a distributed processing cluster. It's lazy, meaning that no processing is done until it is absolutely necessary. So until the value is needed, nothing is evaluated. And it's immutable because the data, you can't modify an RDD. All you can do is evaluate something new from it and gain a new RDD. And so these three in combination give us our resiliency. Because if any node drops out on the network, because these things are lazily evaluated and they're immutable, we can always recalculate. So it makes it very durable to use in a distributed manner. So what does this look like? Let's say we start with a data set. We have a really small array here, 5 numbers. And what I'd like to do is count how many of these numbers are even. So the first thing I do is I'll tell Spark to parallelize this operation. So I want it to take this array and turn it into an RDD for me. And so what Spark is doing now is it's preparing to get this workload ready to be distributed. So now I've got an RDD. Right now it looks kind of the same, except that I've changed the graphics a little bit. So now what we can do is we can tell Spark we would like to run this operation on the entire RDD. In this case, we're looking at something called the filter operation. And filter will take a function. In this case, I'm telling it I want to pass this lambda, this is little Python code. For every value that comes in, if it's modulo 2 equals 0, it's even. So this is pretty much, we know this. And what will happen is I'll get a new RDD that just contains these 2 values. And so then what I can do is I can tell Spark to count those for me. And now I know I've got 2 of these. So there are many more operations like this. There are map functions. There are reduce functions. There are all sorts of different applications you can do to the RDDs. And we'll look at this pattern over and over again throughout the course of this presentation. So what's a Spark application? In general, this is the way I kind of think about it. You've got some source data. It doesn't necessarily have to be in a database. It could be in a stream. It could be in a file. It could be coming across a socket. And you're going to process that data and then create some sort of results from that. And those results could be consumed by a web application. They might be consumed by another processing application. I'm using very loose terms here because your needs will be very specific to whatever application you're creating. So here's a very simple Python program. And what I'm doing is the same thing we just looked at here. So you can see I've got this parallelize operation that's taking some data on line 8 there. And that would come from input on the command line. So if we look here, I'm just taking the first argument that I passed to this script, which will presumably be a number. And this program is pretty bad because I'm not doing any error processing or anything. But I'm going to parallelize that. Once I make a range out of it, I'm going to parallelize that. And then I'll do the filter operation like we just saw. And then finally, I'll count it. And lastly, on line 12, we'll just print something out. So what does this look like when I run it? This is going to use the Spark submit command. And I'll just type in simple.py, and I'll tell it I want it to count 1,000, from 0 to 999, and tell me how many of those are even. So Spark starts going. There's a lot of output. How am I supposed to use this? What was the value that it even returned? And you can see embedded up here is, out of 0 to 1,000, there are 500 even numbers. Okay. This isn't very useful if I want to put this into the cloud. This may be okay if I do it, on my desktop and I'm just practicing and I want to see if my program works. But if I put this into a container and push it up to, Google Cloud Platform or Amazon, how do I get this result? I'm not going to parse the logs. That's outrageous. And it gets even more outrageous when you think about a more complicated application. So what you're looking at here is the architecture for an application that myself and a few of my colleagues sitting here put together. And this is a basic recommendation engine, okay? So you can imagine something like Netflix, where I go and look at a movie and I rate it, and then when I want to find a new movie, Netflix will tell me, oh, you might like this. So there's just a simple HTML server, there's kind of this data flow, and these pieces here might be Spark applications that will do the actual processing to make this recommendation engine. So when I start to think about designing something for a microservice for Spark, this is the process that I look at. And it looks very similar to what we saw earlier about the data and process, then results, right? I'm going to ingest data from some sort of source. I may not know what it is yet. It will depend on the requirements of the application. I'm going to do some sort of processing on that data, and then I want to publish the results to somewhere else. And I might be publishing them to a web server. I might be publishing them to another microservice. I might be publishing them to a text file somewhere. This will all depend on, how you're building it. On top of that, I really consider the structural needs of how the application will be put together, right? So how are you going to deploy the individual pieces of your application? Once they're deployed and running as containers, how will you control them? How will you send commands to them? How will you shut them down in a timely fashion? How will you get results? And likewise, thinking about the input sources, where data is coming from, and then the output sinks. What is the architecture that you're going to have to write your application for? Because that will affect how you write your application. So one style of doing this we call on-demand batch processing, right? So again, we've got a data source, we've got some sort of processing, and this will only happen when there are requests to make that occur, right? And those requests, they could come from a user saying, what movie should I watch? They might come from another program that needs to ask for information periodically. But the point is that the processing only happens when you ask for it to happen. And so here we're looking at a function that comes from an application that we have in our GitHub repository that's just a simple pi calculator. So we're gonna estimate the value of pi based on a technique that randomizes points in a fixed space. And it says if these points are inside a circle or outside, I can take the ratio of those to determine a loose approximation of pi. And if we look, though, here on line 13, you can see we're doing something similar that we did before. We're going to parallelize a stream of data. So one of the things you can do with this is you can see at the top, I'm taking the scale value, and then I calculate this n. So I'm telling it how many points would I like to use? How many random points will I try to estimate inside or outside the circle? And so this parallelize will just create a list of those. And then the next thing I'll do is map a function onto everything in that list. Now, I don't care about the values of the data because, if this xRange function is going to make a list, it's going to be like 0, 1, 2, 3, up to 10,000 or more. But I don't really care about the values. I'm just using that as a source for a counting number. What I actually want to do is what's in this function here. I want to make a couple random points, and then I want to return this value of whether they're inside the circle or outside the circle. And this map function will actually distribute this function across the entire processing cluster. So what I can do is scale the cluster up. As a user asks for more and more points, you can make this more dense. So this is a very simple example, but this kind of shows you how you could do it. And then lastly, we reduce just by adding together all these values. And then, kind of here on 16, 17, and 18, we're determining pi based on, the formula that we have. And then we just return the value. Okay, so this is a very simple function. Every time we call it, we'll get back a value of pi. What we can do is encapsulate that into an HTTP server, right? So this is a simple Flask code, and this is part of the tutorial code we have up. And you can see that this is just an endpoint that you can hit with HTTP, and what it will do is call that processing and then send it back. Okay, so pretty simple, and this is actually probably too simple. You wouldn't want to use this kind of thing in production. Can anybody see a problem that might occur from running this like it is? What happens if that calculation takes more than 2 minutes to complete and someone makes an HTTP request for a pi value? They're going to time out, right? So it works. You can test it this way, but you might run into a lot of issues. It could throw an error, and then we'll just get a 500 back. We're not even processing anything here. Another way you might do this in this style is using gRPC, which is very popular now, a more binary protocol for making remote procedure calls. This is another way I could expose it. And you can see Although there's a lot of extra code here, and we've added some threading around it to make sure that you can't double hit it and whatnot, we're still doing the same thing. A user makes a request to get pi, they send in the scale, we calculate this value, and we're doing it as they wait, and then it gets sent back. Now, gRPC is a little more resilient than HTTP, so you could have long times without timeout, but this is still probably not the best way to do this. And we'll get into a little more how you can separate those concerns later. Another style of processing is what we refer to as continuous batch processing, right? So before it was on demand. Every time someone asks for it, they'll get something back. In this mode, you're always processing. Maybe you have data coming in, and you always want to be refreshing the processing that you're doing and then store the results somewhere. And what that might look like is this piece here. Now, we saw earlier that recommendation engine, and one of the components was called the modeler. So as people make ratings in something like Netflix, the model that's created to predict new ratings has to be continually recalculated. So what we're looking at here is just a simple loop. And at the top on line 2 and 3, we're trying to select new ratings from the database that our front end is making. Every time a user makes a rating, they put it in the database. So we're looking to see, are there any new ratings? If there are, then what we should do is start doing some work. And you can see, again, we're parallelizing the operation. So we've got the new ratings now, and we're going to parallelize them. And then what we're going to do is we're going to take those ratings, and we're going to apply this map function to them. Now, in this case, we do care about the values in our data stream. And this mapping function is just going to pull out some of the values so that we can process those. Ooh. And then what happens is we go down here, we take the values from the ratings, and we pass them into our modeler. And this is where we're actually doing the training. So the work is actually happening here. And then in the end, we write the new model out to a database that will be used by our prediction engine. And if nothing has changed, we just sleep for 2 minutes, and then we try again. So in this style of application, I'm not really interacting with it. I might have a control channel to shut it down or just see if it's healthy or something. But really, I just want it to run all the time. I just want it to continually calculate new models for me, because this is going to be part of a larger application pipeline that I'm running. So another type of processing aside from batch, and this is very popular now, are people here familiar with Kafka or AMQP or other kind of messaging formats? So stream processing takes its source data specifically from a stream of events, which means you're not looking at data at rest, you're looking at data in motion. And there are different abstractions that Spark uses to process these, but it's similar in some ways. And so the way I visualize it here is, you have source data coming in on a stream, and a very traditional way to look at this is to process it and then store the results in some sort of sync. So maybe you're watching log files that are coming off of a server you have somewhere, and you want to parse those log files to see maybe when a user is trying to log in and they failed to log in. So you're writing a security application. In this style, you would have your processing loop always looking for information coming from there and then storing results. And maybe it says, oh, this machine someone's trying to break into. So let's look a little deeper into that. One of the ways you can do this in Spark is what's called structured stream processing. And this is how we might set up a structured stream. And so you can see, I'm getting access to the Spark session, and then I start to set up this kind of complicated interaction here. So I'm going to have it talk to Kafka. I'm telling it where the servers are. I'm telling it what topic to subscribe to. And then I'm starting to see some SQL here. So I'm telling it what do I want it to do to that stream. So in this case, I want it to cast every value that comes across as a string. And then I want to group those values and count them. Then I'm going to write the stream out, and I'm going to store it just in memory under a query called results. And then we tell it to start, and it goes and starts processing. And this call is non-blocking, so this will go, and then you can go do more things. But the important thing here is how you're starting to structure this. So now we've got this, it's in memory somewhere. How do I get access to it? No, sorry. I have another function, maybe in another part of the program, and I want to see, so that previous example was counting values that come across a stream. So we're looking at words, and we count up how many instances of each word we see. And this function, we want to find out what are the top words that we've seen. So I could call this from anywhere in my application, and you can see that I'm going to use this SQL command in Spark to actually directly run an SQL query on it. So I'm going to select everything from results, like we saw earlier. That's how we're grouping them. And I want to order them by the count, descending from, so we want to see which ones are the top rated. Then I'll collect all those results. And collect is an operation that allows you to pull results from the executors back to your driver program. So once I collect them, now I've got an RDD that I could actually look at and say, okay, this is what you just pulled off the stream. And then finally, we're going to return these lambdas and the maps we have at the bottom. These aren't Spark maps. This is just a Python map. And I'm just pulling values out because I only want certain values from the data stream. So, is anyone here familiar with the Kappa architecture? Has anyone heard that term before? No? Okay, so Kappa is another way, so people refer to the lambda architecture, where you have kind of a function, takes input, passes output, another function. You can kind of chain functions together. At some point, and I'm blanking on the name now, this term was kind of thrown out recently about the Kappa architecture. And in Kappa architecture, everything is a stream. So information comes in on a stream, I process it, and then I put my results back out onto maybe the same stream or a different stream. And by doing this, it gives us the ability to interact with the data in a different way and to build applications in different ways. And so what this might look like, and this is an application that will filter a stream of words that is coming in. And every word that comes in on the stream, it will apply a regex filter to. And if the word passes that filter, it will take that word and pipe it out to a new stream. So you could imagine that if this was our log stream from earlier, and we were looking at some sort of like Linux logs, if we saw security messages, maybe we knew we were looking for a bad login attempt, we could pull those values out, and then we could watch the second stream, and we would know immediately when things are happening in the primary stream. And so you can see here, we've set up kind of this. I should have said this a little earlier, but this is using a different style of streaming. This is not structured streaming. It's what's called direct streaming. So you can see here I've made this thing called the direct stream, and I'm plugging it into Kafka, and I've told it the topic and the server to talk to. And now what I can do is I can make these operations, and as I tell it to map this map operation on the Kafka stream, and I'm telling it how I want to do all these operations, Spark won't run them immediately. Spark is queuing up a series of instructions that will execute every time this happens. So these aren't happening right now, but they're actually setting up the workflow inside Spark. You can see here, this is where our filter is actually running. So I've taken the words, I've pulled them all off the stream because I know that they're coming in on the stream as like a pair. There's like a front pair and a second pair, and the second one is the word. And this has to do with the details of the application. But then we're going to filter those, and this is where we're running the filter. Now, at the bottom here, you see this. We have this for each RDD. Run this send response command. So what happens is when I start the stream, every 3 seconds, it's going to collect an RDD. And it's going to take that RDD and pass it into this function that I've written here. And so this function then will be able to look through and say, okay, if there are values in this, meaning it's passed these filters, we'll get an RDD with values in it, and we know we need to send those RDDs to the second topic. So how many people here use Fedora? How many people here have contributed to Fedora? Maybe bug reports or code? How many people here have seen the Fedora badges? Okay, some people. Okay, so you guys are kind of familiar. There's all this information happening in the Fedora world. And really, Fedora has been doing Kappa before all the cool kids started saying Kappa is better than Lambda. And that's in the form of the Fedora Message Bus. So you may or may not be familiar with the Message Bus, but in Fedora, there's a stream of events that looks like a log. And for anything that happens in the build system or with bug reports or when a new badge happens, there are different processes that read and write from this stream, and they pass information along that way. And so you can imagine, whereas earlier we were looking at the batch processing and we had one data source, one processor, and then an output source. In this manner, we can have several processes all attached to the same stream of data, and then different applications can do very discrete things with the information they're looking for. So in this way, you can approach something closer to the Unix philosophy of writing applications, which is to do one thing and do it well, right? So I don't want to write a monolithic application that has to process, all these Fedora Message Bus, everything from Meatbot. Koji is a build system, looking for things coming out of the Apache server. I don't want to write one application to do all that because it's a nightmare to maintain and it will take a lot of people to engineer. What would be much easier is just to write each one as a separate application. You can have different teams working on them. They don't have to change, it's just much easier to develop in a distributed manner in this way. And then likewise, you can write all sorts of different tools that consume the data and do different things with them, like make our badges that we all love. And so this actually helps us to create more innovation, because once this stream is out there, if it's public, any of us in here could go learn how to use the Fedora Message Bus and write an application that can read from it and do something with it. So you can make a web server that puts up your own displays. So now we start to distribute the work even more, and we can kind of open up creativity. So how do we integrate Spark on OpenShift? I'm gonna switch gears a little bit now and kind of talk about some of the tooling that the group I work with at Red Hat has been working on. We have a community project called Rad Analytics, and one of the tools we make is something called Oshinko. Now, in OpenShift, there's a concept called source to image. And basically, there are builders that allow you to say, here's my Git repository. So in this case, we assume we have a Python-based Git repository. And I can tell OpenShift, I want you to take the latest commit, or I want you to take this branch or this commit, and I want you to build that application into a container. And what we've added is a piece that will actually deploy Spark for you at the same time. So now when you make your application, I don't really even have to think about the infrastructure. Because by using Spark's API, it will know where the master and the workers are, and I really don't need to be concerned about the URLs of how do I attach to those. This tooling will just allow you to automatically do that. Likewise, we have a graphical utility as well that will allow you to view the clusters that you've created, and in a very easy way kind of increase and decrease the number of workers, or create new clusters, or delete old ones. So it's another way to look at this. So what I'd like to do now is I'll show you kind of how this works. And I've got this repository here. This is the Pi estimator that we were looking at, right? And it's very simple. It's just one file. And there are some instructions here that I need to go through in order to get my project in OpenShift ready. So switch here. Hopefully that's not bad. Let's just make sure. All right, cool. All right, so I'll double check that I'm logged in. I am. I'm going to make a new project. If I can type, which I can't. I'll call it devconf. Now hopefully, okay, if the Wi-Fi starts to misbehave, I'm going to switch to a video, but hopefully it will keep behaving. Now the first thing I want to do is run this template. And in OpenShift, much like Kubernetes, there are manifests that look like JSON or YAML files. And those manifests tell Kubernetes what you would like it to do. And it's a declarative system, so I tell it, I want you to make 4 pods, and pod 1 should have this, pod 2 should have that, pod 3, etc. And what the system will do then is it will either deploy it, or it will fail, or whatever. And so the first thing I'm doing here is I'm setting up some objects that I would like my project to have so that I can use this tooling. So I'll just copy that. I don't know how we're doing on time. All right, great. So now you can see I've created some objects inside of my project here. The first couple, I've made a service account so I can do work. I can have it do work for me to create new pods. And then I've created some templates for the different types of source to image builders that I have and for the web UI. And so the next thing I'll do is I'm just going to copy this line here. And this OC new app is a way for me to engage the underlying source-to-image mechanisms that are in OpenShift. And so I'm going to tell it to make a new application. I want it to use this Python, this PySpark template that we have I'm gonna tell OpenShift what to call my application just to make it easier for some of the commands. And then the last thing I tell it is, where do I want it to find the GitHub repository for that? And so what we'll do is we'll just copy this. We'll start running it. Okay, so boom, a bunch of stuff was spit out. What's happening? Well, at the bottom here, you can see it was a success deploying what I asked it to do. It can do that. And if I want to see what's happening with the builder, I should run this command to follow the logs. So what I'm going to do is follow the logs, and we can see, I'll back up because this went by kind of, this building very quick. So you could see it at the beginning of these logs, it was cloning my Git repository. I know what commit it was pulling. And then it starts building the application. You can see I've got some requirements. I'm using Flask. It's installing the Flask requirements. And at the end, once it's done installing Flask and the image is created, then it starts to push the image to a local registry in my project. And so now I've got an image. What I can do next, actually, before I do that, I'm going to expose it. So what I'm going to do with this expose command, this allows me to tell OpenShift to create a DNS entry at the edge router for OpenShift to associate a domain name with the service that I just created. So I have a service wrapping my HTTP application, and I'm going to tell OpenShift now to create a linkage to the external router so that I can get a domain name associated with it. And the demo that you're looking at here, I'm running this in Google Cloud right now. So this is OpenShift running on top of Google Cloud Platform. So I'm not running it here on my laptop. And you'll be able to see from the URLs. So I can also look at the logs that are coming out of my application. So what are we looking at here? You can see at the top the Oshinko tooling that I'm using, the Spark cluster image, where that comes from. And then it says it didn't find a cluster. So I could tell it a cluster to use if I already had one set up. But in this case, it didn't find one. So it's going to create an ephemeral cluster for me, which means that cluster will live for the life cycle of my application. And when my application goes down, it will delete the cluster. So it'll clean up after itself. And then we're waiting for the cluster to become available. It's all available. And now it's running, waiting for requests. So how do I find out where it is? I'm going to split my terminal here so we can watch the logs coming from there. Because what you'll see is something similar to when we ran the application earlier. So to make things easy, I'm just going to copy these curl commands because there's a way for me to learn the route. There's a way for me to learn the route by querying OpenShift. And so I'll just tell it, okay, now I see this has come back from my application. You saw we got the request here, came in, a GET request at the root, and I got back this. It says we're running, Flask Spark Pi is running, add Spark Pi to the route to this URL to invoke the app. Okay, great, let's try that out. So I take this command, I add Spark Pi to the end. Okay, great, now we're seeing a bunch of activity happening here. What's going on? And this goes back to what we said earlier. You see the wait that took for that to happen? But we got our answer. Great, okay, so this works. We can see how this is working. I want to show one other thing, and I know I'm starting to run low on time, so I'm going to try to keep it quick. But what I'll do is I'm going to start the web UI, and I just started it by running the new app command. And now I can switch back, and now we're looking at the OpenShift console. This is the web interface, and this is what my project looks like internally. You can see that this is the Spark Pi application. These are the clusters it deployed. And what I'm waiting for it to do now is I'm waiting for it to install the web UI application for me. So probably what's happening is it's probably pulling the image from Docker Hub or something right now. Because oftentimes what happens is when you've got a distributed cluster with Kubernetes and you're trying to pull images to new nodes in the cluster, it might not have that image cached already. So probably I'm hitting one that I haven't got to. Oh, and it looks like maybe it's failing. Oh no, it's up. All right, great. So click on that. And this is, now I've got like a little cluster manager tool. And I see the cluster that's present, the Spark cluster that's present. I see what the master URL is. So if I wanted to connect to that with another Spark application, I could. How many masters, how many workers. I can drill through to the actual Spark UI. So if I need to see what Spark is doing, this will give you internal metrics about how Spark is operating. And as you learn more about Spark and as you start to use it more, this will probably become more important because you'll want to drill in and see how is it failing, how is it performing, that kind of thing. And then likewise, I could do something like I could scale the cluster up if I wanted to. We don't really, for what we're doing, we don't really need a lot of processing power. But if I wanted to, I could scale it up to 2 workers. And if we look back here, we can see that my workers have already gone up to 2 pods. So it's interacting with OpenShift. It's helping me to manage that cluster if I'd like to use that. I could use a command line tool to do the same thing. There's several different ways to access this. All right, so back to here. So we talked about synchronicity, right? Making a request, waiting for the response, and having it come back. So I ask it, what's pi? It sends me back a request. But as we noted, there's problems with that. So how do we move to asynchronicity, right? And this probably will not be new to many of you, but we make a request. Now we get back this. Well, that's not pi. That's some sort of ID. And that ID is the ID of the transaction we just made. So then I can request what's the status of this transaction. And if the processor is still working, it could return a value that says, I'm still working, ask again later. Or if it's done, it could just give me the answer back. So in this way, now we start to separate the concerns. And what that looks like is this. We now have 2 processes in our application. We have the main process that's taking API requests, and it's communicating through inter-process communication to the analytics process. So we're starting to pull these things apart and make a more complicated application. But with that main process, we can do kind of interesting things now. We can make different routes that could tell us the health of what's happening. They could command the application to do something different. It's kind of endless. And so what that looks like in Python is we use the multiprocessing package. And I create these queue objects, which allow me to do inter-process communication. Then I'm going to start my process, and this is the loop that I'll have it use. And I'm going to pass in those queues. I start the process, and then I'm going to wait. This is a blocking call. I'm waiting for the other process to start up. And this is my loop function. You can see I pass in my queues. We see some similar stuff up here. I'm getting the Spark session again. And the first thing I do once I've got my Spark session is I tell the main process I'm ready. So I'm communicating back to the main process. And then I go into a processing loop here. Now I've taken out a lot of the code. If you go look at, this is actually for the recommendation engine. This is a piece of code that comes from the predictor engine. So because the predictor engine was not running in a continuous batch loop, it needed to communicate with the front end because it would only make predictions when you request them. So I've taken out a bunch of the code to make it simpler. But you can see the first thing we do is we tell the main thread we're ready, then we enter our loop, and then I block here waiting for a message to come in, waiting for a request to do work. Now, I might get a request to stop. You can see now I can have a timely, kind of orderly shutdown of my process if I want to. Or if I'm not being told to stop, I'm being told what type of prediction to make. And so I do some work. I come up with some sort of response, and then I put that response back to the main thread, and now the main thread can communicate that back. And in this case, we have a transactional ID that we're using, and the main thread keeps track of all that for us. But it's separated from all the processing concerns that we have. So another piece to this, as you can imagine, is that we're distributing code across a network. Dependencies can get really hairy. And Spark in specific, especially with Python, you need to make sure that your dependencies are prepared properly because in Java and Scala, you can tell it to pull packages from Maven Central and that will install them on all the executor nodes. In Python, you have to be a little more explicit about it. And I guess maybe that goes to Python's explicit versus implicit, who knows. So I've created a really bogus application here, and I don't have a link to the code because you should never, ever do this, okay? Because what I'm doing is I'm creating my Spark session, I'm giving it some data. This is the same application we saw before. We're counting evens, right? But now what I want to do is management says that we're going to have a stream of data, and I want you to store the counts of all the values we see in a database somewhere. And so what I did was I put my database transaction in this function that I'm going to distribute. So you see I'm parallelizing my data. I have a filter function, and I'm passing this filter evens in. And you can see I'm instantiating a Mongo client within this distributed function. So this function is going to be pickled and sent to the cluster, and it's going to do all this work accessing the database and trying to make counts and everything. Not only is this bad design, but what's going to happen is unless I have PyMongo installed on every executor node, it's going to fail because it's going to try to import PyMongo, and it's not going to be there. So this is something you have to think about if you're designing applications, especially in this mode. You'll have to create images that already have the dependencies you need on them, or you'll have to use one of the command line options in Spark to send those packages. And Spark does not have the best Python tooling yet. I mean, it's fun, it's good, but like, it's still difficult to distribute packages very easily. You have to put them into zip files or send the Python files over manually. So it's cumbersome, but it's doable. And so with that, I'd just like you guys to kind of consider some of these things. You know, this is the basic application architecture we're looking at. This is our mechanism for deploying to the cloud. And this is how we can separate the concerns in our application. This QR code will give you a link to this slide deck, so if you want to download it and look at it, take it apart, everything in there is open. And I invite you to go to radanalytics.io. All of our tooling is there. We've got tutorials on how to use this, and much of the code that you looked at today is there, and you can download it and play with it and tell me how bad it is and send me issue requests, and and I'll get mad and pull my hair out or something. Well, hopefully not, but So yeah, so thank you, and I'll take any questions if you guys have any. Question?
I would like to ask, is there any way of auto-scaling the workers of this Spark? You set up the cluster using source to code, source to image, or
yeah.
the name exactly.
Yeah.
And you are showing that you can specify in an interface of OpenShift that number of masters and number of workers.
Yeah.
Can this be automatically scaled?
Yes, that's a good question. The question is, can Spark be automatically scaled? And the answer is yes. So there are a couple ways this can happen, but we've written some tooling that's in the Rad Analytics repo, and it's called Scorpion Stare is the name of this application. And what you can do is you can read the metrics that are coming from Spark, and Spark will let you know through its metric interfaces when it doesn't have enough executors. It will tell you how many it wants and how many it has. And then what that tooling does is it communicates with OpenShift, and it says, if I see that this thing it doesn't have enough executors, I'm going to tell the Oshinko tooling to add more workers, right? So it will automatically talk to the cluster for you based on the metrics coming from Spark. Okay. And that runs as another service inside your application. So we haven't bundled it in. We're using kind of the cloud native approach to make another microservice that can help improve the action. So you can have it or you don't have to have it. There are other methods too that are coming with Spark, or they're coming with Kubernetes that will do auto-scaling based on CPU usage. But Spark is a platform that uses a lot of memory. It keeps everything memory resident. And sometimes CPU usage is not the best way to measure if it's starving, right? So that's just because in Kubernetes, they're just looking at pods as like generic processes, right? But with what we're doing, we want to look exactly at the Spark metrics, and those metrics will inform us exactly what's happening inside. So there's some tooling out there. It's kind of experimental right now. I'd say it works, but it's in like an alpha beta state. But you could look at it and see exactly how it's being done.
Okay. Yeah, thanks.
Cool.
It's probably using its alpha version of custom metrics scaling in Kubernetes.
No, so what it does is it attaches to the metrics, it reads the metrics port from Spark. Every Spark process will expose a UI like we saw, the web UI. It also exposes a metrics port, and there's other ways, like you can connect it to Prometheus and things like that. Yeah, so we're reading it from Spark, not from Kubernetes. But I think what we'd like to do eventually is make something that will connect the Spark pods that we have directly to the Prometheus that comes with Kubernetes. And so those metrics will be in the main Prometheus installation that you would associate with the Kubernetes cluster, basically.
Sounds great. Thanks.
Any other questions?
Yeah, so when you were doing the streaming processing, it was essentially batching every 3 seconds and then parallelizing that out to the Spark workers, right?
Yes.
Could you just like round robin the stream to a number of workers rather than doing this batching and unbatching? It just seems a little like redundant, right?
Yeah, that's a good question. I'm not 100% sure. I mean, I'm not sure that you're, sorry. So the question was, when we're stream processing, we're actually doing microbatching at a certain interval, and it's being distributed based on the microbatch. Is there a way that we could be more declarative about that and actually tell it where to send work rather than just like letting it microbatch it out, and we can treat it in a different way? So yeah, that's a good question. I'm not entirely sure about the ability to tell Spark where to send work. That may be possible. I'm just not sure. Maybe we could follow up, after or something. You could send me some email or something. We could figure it out. But yeah, I'm not entirely sure that that's the case. And the reason we would do it with the stream is because I want to read from a stream source. So like if the data is coming from Kafka, I want to attach Spark directly to Kafka. And if I were doing it kind of the other way, like if I wanted to actually make a batch process, then I would probably have to have another service that reads from Kafka and puts the data to rest somewhere, whether it's in memory or like an in-memory store like Infinispan or something, or whether I put it into a database or whatever, and then my Spark process would run. So you'd be talking about adding another service in to persist the data. The reason I use streaming is so that I can connect directly to those data sources. So because it is micro-batched out, so yeah. Any other questions? All right, thank you very much. Oh, and if anyone wants to write in a lease saver, please come grab one. But I'll put them up here. Hey, nice. Thank you.